So continuing the previous series that we had, we'll be starting with chemical kinetics. Average rate of reaction is delta concentration by delta time. In instant rate of reaction is instantaneous. It's dc by dt. Then we have this reaction. Let's say is a placeholder reaction. Rate of disappearance of A is minus dA by dt divided by A. All right. So like that, and your rate of reaction can be given by rate of disappearance or rate of appearance divided by stoichiometric ratio. Then your molecularity, which is no meaning for a complex reaction, and you probably know what it is. Order of reactions, here I've written some. Zero order, first order, second order. We know dr by dt, the differential rate law and the integrated rate law. I won't be writing that here because this is very basic. You should be knowing that much. So R naught by 2k, ln 2 by k, and 1 by k into R naught is the half life. Examples of these reactions could be H2 plus Cl2 gives 2HCl, that's your zero order reaction. HI in gold surface gives H2 plus I2, this is also, I think, is then NCRT. It forms that weird bonding thing that they've given, right? Under, it's there basically. Okay, so H2O2 decomposition is a first order reaction. Radioactive decay is also first order reaction. Then second order reaction, we have CH3CO C2H5 with NaOH gives this, and C2H5OH. Basically, OH minus is attacking nucleophilically attacking the what do you say, C double bond O and kicking it out. So yeah, and then we have hydrogenation at 100 degrees Celsius in presence of H2. C2H4 becomes C2H6. That is also a second order reaction. These are some things that you might have to remember. I'm not sure, but just go through them. T 3 by 4 is equal to 2 T half. That is a trick that you can use. T of 87.5 can be stated as equal to 3 TeV T of half, meaning half life, and T of 99.9, this is also given in NCRT, is equal to 10 T half. You have to use it carefully, okay? Don't use it for 99, don't use it for 99.99. I mean, maybe you could, but like, don't use it for 99. That's what I'm saying. Amount of substance left after n half life, this has been come in PYQs many times. So it's A naught, initial concentration, divided by 2 power n. Nth order reaction, your T half is proportional to 1 by A power n minus 1. Apart from this, you can derive the integrated rate law if you want, but I'm not going to write here. Parallel or side reactions, we have K1 plus K2T is equal to ln A naught by AT, and B, concentration of B by concentration of C is equal to K1 by K2. So now this is what um yeah, these kind of reactions, right? A producing B and A producing C. We have percentage yield of B is K1 by K1 plus K2 into 100, and percentage yield of C is K2 by K1 plus K2 into 100. Okay, so basically directly PYQs has been asked on this, so make sure you have marked it up. Series and consecutive reactions, T max is equal to 1 by K1 minus K2 ln of K1 by K2, and these are the reactions that are proceeding. A gives B gives C with K1 and K2. Okay, so this is the actually the, I think, rate law. So anyways, we have Arrhenius equation, which is K is equal to AE power minus EA by RT, that everybody knows. Catalyst decreases EA, and A is pre-exponential factor. Now here's some NCRT points that you guys must have missed. Pseudo first order reactions, they have given an example called inversion of cane sugar, which is, you know, your pseudo first order reaction. And then this reaction is specifically given in NCRT, saying that MnO2 is a catalyst. So KClO3 gives KCl plus 3O2, where MnO2 behaves like a catalyst. Okay, then you have a temperature dependence of a rate of reaction. In decomposition of N2O5, time taken for half the original amount. This is like some stupid fact based stuff, but we know that potassium permanganate and oxalic acid, permanganate get decolorized faster at a higher temperature than at a lower temperature. It's given in the titermetric analysis NCRT. For a chemical reaction, the rise in temperature by 10 degrees, rate constant is nearly double. This has been directly asked in statement based, so please mug it up. Increase in 10 degrees Celsius, double rate of reaction. Okay, then we have like the Arrhenius equation that I just explained. It's also called frequency factor. It's also called pre-exponential factor. And then I told you, right, the reaction is given over here. H2 plus I2 gives Hi, 2Hi. That's also given. And according to Arrhenius, this reaction can only take place when a molecule of hydrogen and a molecule of iodine collide, okay, to form an unstable intermediate. So that's what. So then you have the energy required to form this intermediate called activated complex is known as activation energy. Right? Everybody knows what is activation energy. How to calculate, your activation energy from the graph. I think that's all self-explanatory. Then we have this graph, which is your, I think, what is it called again? Some I don't know, man. Maxwell graph, I think so. Anyways, so this graph represents fraction of molecules in the y-axis and kinetic energy on the right x-axis. You just have to remember the shape of this graph and what is the use of it. So basically, it corresponds to the most probable kinetic energy of like basically, as you see, the peak is at this point, right? So the what do you say? The kinetic energy will peak somewhere in the middle, and that's when the most fraction of molecules will have this kinetic energy. So yeah, that's all is written, and you need to know what happens with temperature increase. If temperature increases, peak shifts towards the right. So this graph will go, I mean, this will go something like this, and the area under the curve will always be constant. All right, area under the curve doesn't change. The curve changes in shape and size. I mean, doesn't really change in size, right? It just shifts, and the area just gets broader. Like this area is just distributed in a different way. So the area of the curve stays the same, but the curve becomes flatter and wider. Okay, then you have effect of catalyst. See, I told you, right, the MnO2 thing is there in NCRT. Catalyst provides an alternative pathway or reaction mechanism by reducing the activation energy between the reactants and products, and hence lowering the potential energy barrier as shown in the diagram. So here it's showing that it's like this. And remember alternate pathway because it's been asked as a I think it's an exemplar. Anyways, then we have catalyst does not alter Gibbs energy. That is something that we need to remember. I mean, it's kind of obvious. And then it catalyzes the non-spontaneous reactions but does not catalyze the sorry, it catalyzes the spontaneous reactions, but it never catalyzes the non-spontaneous reactions. Okay. Catalyst does not change the equilibrium constant of the reaction. It helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as backward reactions to the same extent, so that the equilibrium state remains the same, but it's reached earlier. That's what it's trying to do. Okay, so I have collision theory. Collision theory is pretty basic. According to this theory, the reactant molecules are assumed to be hard spheres, and the reaction is postulated to occur when the molecules collide with each other. Remember the hard spheres point. The number of collisions per second per unit volume of the reaction mixture is called as collision frequency. And yeah, so it's almost the same equation. You just replace A with your collision frequency, ZAB, and it's somewhat related. Okay, A is related to collision frequency. They have given this in NCRT. The collisions in which the molecules. So one thing this is the reason, like basically they are saying that this equation predicts the like the rate constants accurately for reactions with involve like simple stuff, but complex stuff it deviates. This could be because all collisions do not lead the formation of products in the complex reactions. Okay, so the collisions in which the molecules collide with sufficient kinetic energy called threshold energy and proper orientation. Proper orientation is also a term that it needs. All right, remember that. So to facilitate breaking of bonds between reacting species and forming new bonds to form product is called as effective collisions. So yeah, that is your effective collisions. So here they've given an example of CS3Br with OH, and if there is improper orientation, there is no products, and because they will bounce back. All right. I mean, that's kind of stupid, but you know what? It's fine. To account for an effective collisions, another factor P called the probability or steric factor is introduced. It takes into account that the fact that in a collision, molecules must be properly oriented. Okay, so PZAB comes. So that's your steric factor. So collision theory and activation energy and proper orientation of the molecules together determine the criteria for an effective collision. and hence the rate of a chemical reaction. Collision theory has also certain drawbacks and blah blah blah. They are assumed to be hard spheres and ignore the structural aspect. So you know what? That is fine. I mean, it's just telling us. So here you just you just calculate e power minus ea by rt in this question, and you're done, man. That's all you have to do that, and you calculate that stupid e power. I think it's minus 41 that you get from here. It'll be something 10 power minus 19. That's the answer you get over here. It's given in NCRT. I just want to put it because they ask it in mains, we're fucked because we don't know e power minus 41, and I'm pretty sure NTA fuckers won't give that shit. Anyways, we have electrochemistry. Electrolysis, Faraday's law, W is equal to Z cubed, Z or ZIT, Z is equal to M by NF, where N is N factor. Um, Galvanic cell is prepared by zinc rod immersed in ZnSO4, anode, C rod immersed in CuSO4, cathode, salt bridge, U-shaped tube of inert electrolytes, KCl, KNO3, NH4Cl, NH4NO3, agar solution. Cation and anion of inert electrolyte have same mobility, okay, same mobility of inert electrolyte, cation and anion. Ions of inert electrolytes do not mix with the electrolytic solution present in half cell, which is kind of obvious. Ions of inert electrolyte do not participate in electrochemical change, which is also obvious. Functions of salt bridge. All right, you have functions which is completing the electrical circuit. I'm pretty sure everybody knew that, and maintains the two half cell electrically neutral by the flow of ions. All right, that's how you have to remember it. And temperature coefficient of the cell is dE by dt at constant pressure. I mean, I don't know if they'll ask this, but you know what? I just put it. Concentration cell, you have basic Nernst equations. You just put it for C2 by C1. This is for electrolyte type. You just do C2 by C1, and you can easily derive these by just writing the equations. Okay, I'm just summarizing everything. E cell is equal to 0.059 by 2 into log P1 by P2. Important types of electrodes, we have Calomel electrode, which we can say that this is the equation for the anode. You can write the cell reactions as well. They're very simple, like Hg in liquid reacts with 2Cl minus to form Hg2Cl2, which is a solid with 2 electrons released, and cathode is just opposite of that. Then we have there's a general formula for any metal insoluble ion type cathodes and anodes. We can just mark this up and we are good to go. I mean, obviously you got to balance it if it's not balanced, but yeah. Then we have primary battery. Very simple. Reaction only occurs once, and after the use, battery becomes dead and cannot be recharged nor reused. Okay, they cannot be recharged nor reused. Construction facts of the basic. I think what is it called? I don't. I think a battery. Like I don't know which type of battery this is, but you know what? Just mug it. Zinc container. Zinc acts as an anode. Carbon or graphite rod is the what do you say? Is not exactly the cathode. Let me explain. MnO2 here, your boy MnO2, that is the one that's undergoing the reduction, as you see over here. So basically MnO2 is the cathode, but carbon is just there. Carbon is a fuck cat. Carbon is a cup. It just wants to be there. So you have carbon powder, or like along with MnO2, and you have a graphite rod. Alright, so electrolytic place contains NH4Cl and ZnCl2. Reaction is zinc becomes zinc 2 plus plus 2 electrons, and you have MnO2 with NH4 plus with an electron gain. Obviously, it's a cathode, right? So it becomes MnOOH, and as far as I remember, this is called hydrated magnesium oxide or something, because then salt analysis, and I think it's a brown colored thing, right? If you guys remember, like correct me if that's wrong. Okay, so yeah, this released NH3 actually reacts with the zinc to form this complex. Okay, tetramine zinc ion. So yeah, and your voltage, average voltage here is 1.5 volts, and yeah, so you have mercury cell, which is your zinc mercury amalgam, and cathode is paste of HgO and carbon. Okay, electrolyte is paste of KOH and ZnO. So your reactions, actually HgO is the cathode, right? Carbons is there, it's a cuck, I told you, right? So ZnHg plus 2OH minus gives ZnO plus H2O plus 2 electrons. HgO plus 2 electrons gives Hg, and that's how the reaction happens. Voltage has to be constant, as overall reaction does not involve any ion in solution whose concentration can change during its lifetime. Basically, concentration of these ions will always stay constant. That's why the voltage also has to be maintained as a constant. Okay, then we have secondary batteries. Okay, secondary batteries, we have lead storage battery, which is the most important secondary cell. Constructions is anode is lead, cathode is lead grid packed with PbO2. Okay, electrolyte is 38% H2SO4. Yeah. So then we have discharging. Discharging is Pb to SO Pb plus SO4 2 minus gives PbSO4 plus 2 electrons. PbO2 plus SO4 2 minus gives um you know PbSO4. So PbO2 becomes PbSO4 and Pb becomes PbSO4. I mean, the product is the same, but just the change in n factor is different. Like the change in, sorry, the what do you say, electrons, the change in oxidation state is different. Sorry, yeah, that you got to mark up because they've asked it. So discharging, it becomes PbSO4. Charging is just opposite of both of these reactions. All right. So yeah, I think that's pretty self-explanatory. Then we have nickel cadmium cell. Electrolyte is soaked in an alkaline medium, KOH or NaOH. And I don't know whether this reaction is important, but you know what? I'm remembering it. CD becomes CDO. NiOH thrice becomes NiOH twice. That's all we need to know. Fuel cells used in Apollo space programs. It's used to generate electrical power. It's used to generate drinking water for astronauts. And the product of the reaction, as you guys can see, H2O liquid is released, so it can be given to the astronauts. Electrodes is porous carbon electrode. Electrode is always a cuck, which is carbon. Electrolyte is conc AQ NaOH. Okay, concentrated aqueous NaOH solution. Your catalyst, which people always send to me, this is NCRT. PT, PD, PDPT, finely divided. Okay, now you have the anode reactions, which anode, just remember, anode releases water, cathode releases OH minus. Then you can just logic it out. Pretty much you can. 2H2 plus 4OH minus gives 4H2O. O2 plus 2H2O gives 4OH minus. Like that, you can say that the fuel efficiency is 70%. Then you have corrosion. Alright, corrosion, factors which enhance the corrosion, presence of moisture, presence of electrolyte, uh, prevention of corrosion. You have barrier protected by oil, grease, or painting, or electroplating. Anything works. Sacrificial protection is also another way, which is mixing a metal with electropositive metal. Obviously, the works are literally common sense. It's so easy. Then you have conductance, which is also another common sense topic. Like there is nothing to discuss in this. We have weak electrolyte, strong electrolyte, graph, which is also explained in NCRT. I'm pretty sure you guys will know it. Then you have alpha is equal to delta m by delta naught m, and you have delta m is equal to 1000 k by s, and this is the centimeter unit. Okay, remember, whatever, they'll give some stupid ass unit in the question, right? That unit is in centimeter. Then we have conductometric titations, which are very simple. SASB, I mean, I'm not going fully in depth. I'm not going to tell how they work, but this is what is like the most basic shit that you have to know. Even though you've not studied this chapter ever, you can mark up these graphs like this, and boom, you're done. That's all. And then you have a question, which is also fairly simple question, just application of what we learned. So we have 100 ml of H2SO4, sorry, CuSO4 is electrolyzed using blah 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 blah. pH of the resulting solution was 1. Keep that in mind. The solution after electrolysis was neutralized, treated with excess Ki, and titrated with 0.04 Na2SO3. S2O3. Volume of Na2S2O3 required was 35 ml. Assuming no volume change during the electrolysis, calculate this. Alright, we have to calculate current efficiency. So what we do, first thing, you have to shut up and write the cell reactions. Don't even think about anything else. Write the cell reactions, write cathode, anode, add them up nicely, put it all up. So you have this and this, you add them up, you make the complete reaction. Obviously, they have said that, I mean, obviously, when you're electrolyting, what do you say? Electrolysis of CuSO4 in aqueous medium, obviously, right? So O2 will release. SO2 will never fucking release because it's a car. Anyways, Cu2 plus with, you'll get the overall reaction, and then you will get concentration of H plus is 0.1, obviously pH definition. Then we have a concentration of Cu is this, right? Then you can get number of moles of Cu by dividing by the number of volume that they've given. Okay, then you can easily use your Faraday's first law just to directly get the answer. And remember, Cu, although we write here that there is 4 electrons exchanged in Cu, the n factor stays as 2 itself. N factor is only calculated from the half reactions. That's like your actual change of electrons. Okay, here this is like the net change of electrons. That's not what you're supposed to count. You're supposed to count only the cell reactions. So whatever n factor is changing in cell reactions, you count that, man. Don't think about it. Just put 2 as the answer. So you put 2 over here in your m by nf. Then you finally do some calculations and you just get the answer directly. And then your moles of Cu, initial moles of Cu2 plus is 0.01 divided by 2. And now whatever, let's say some moles react, okay, Cu2 plus reacts with excess of Ki to give Cu2I2. That is a known reaction. I'm pretty sure everybody knows this, and everybody also knows that Cu plus what do you say, disproportionates with this, but we'll not be considering that here. Okay, so Cu2I2 and releases I2, and obviously the I2 released will react with S2O3 as they've given in the question. Right, so it forms S4O6. This is also a very known reaction. If you don't know this, please, learn it or just kill yourself, right? There's no alternative. So you get 0.04 into 35. That's your number of moles of S2O3, because they've given that in the data, man. Okay, so then you just divide that by 2, because that's the number of I2. If there's 2, you first you balance this reaction. Okay, no one's telling you to not balance it. Balance it, do your full hard work, and then you know what, just write it, man. Just write it. You have 0.04 into 35 divided by 2. That's the number of moles of I2. So obviously that is coming out to be 0.07. So if 0.07 moles of I2 are released in this reaction, that means 0.14 moles of Cu2 plus are left in the solution after the electrolysis has happened. So initial number of moles of Cu2 plus is 14. Cu2 plus, yeah, you can say CuSO4. Doesn't even matter. You have 1.4 millimoles of from this calculation, we'll get 1.4 millimoles. Right, so you'll get 5 millimoles divided by 100, and millimoles doesn't matter, right? Because if you add them, like 5, I'm getting it from the initial moles of Cu2 plus, which we had gotten from the pH value. So from here you can easily get the concentration. Then the next one is the basic application of your calomel electrode. You write the equation of the calomel electrode, you place in the values, and you get the answer. That's how simple. JEE Mains is just going to be like this. Maybe they won't ask calomel, but I'm hoping they do, because half the population will have not an idea of it. I'm not doing dilute solutions, cry about it. There's basically nothing in this chapter. What should I do? Like, I'll just summarize it with words once. We have vapor pressure. Vapor pressure is pressure exerted by the vapors of a liquid. Everybody knows that we have Clausius-Creperion equation, which is your ln K P2 by P1 is equal to delta H vaporization by R, 2.303 R if it's log. And yeah, that's all. Then we have ideal solutions. And then what do you say? Raoult's law. Raoult's law everybody knows, I'm pretty sure. Then you have RLVP. And then what else? Non-ideal, ideal solutions examples, azeotropic mixtures. That and all, everybody knows that graph also, assuming that you guys know. Then you have colligative properties. All of them are very, very self-explanatory. What do you say? Van 't Hoff factor is also very easy. Actual number of moles by moles of solute without dissociation or association. Like that only we can calculate I, right? And I, we can say that the formula is what? 1 plus n minus 1 into alpha for dissociation, and 1 plus 1 by n minus 1 into alpha for association. That's all. Then you get the answer. Then Henry's law is for dissolution of gas and liquid. Very easy. Done. What else is there? So yeah, that's all for the one-stop physical revision. This is the second part. Hope you guys liked it. It's been a journey. That's all. Bye.